This week we have Lerrel Pinto, who's an assistant prof at NYU. Thanks for accepting our invitation, Lerrel. So before joining NYU, he was like a postdoc at UC Berkeley. He worked with Alyosha and Peter Abel. And before that, I guess he did his PhD and master's at CMU. And he's got Best Paper Awards at IROS 2019 and ICRA 2016. And yeah, really looking forward to hear some of your recent work. Over to Lerrel.
Yeah, thank you, Krishna, for the introduction. Very happy to be here. And so throughout this talk, if you have any questions, feel free to interrupt and ask them. I'll be happy to stop and answer your question. So let's get started. So before we start speaking about robot learning, I think it's good to motivate why do we want to do machine learning for robotics. So I think most of you have probably seen this video where you have this Boston Dynamics robot and it's able to do some really impressive stuff, right? It's able to sort of walk around and then it's able to interact with this cubicle block. And it's even able to do so while this human is like hitting it with the hockey stick. And so the first time I saw this video, I was like, wow, this is like really amazing, right? Like, you know, this looks like so impressive. So what are we missing in some sense? So if you look a little closely over here, you will notice a few things. So first of all, the ground is flat, which makes it easy to walk. And then even on the object as well, we have these AR tags on this object, which makes it easy to sort of perceive and recognize the object and then interact with this object afterwards. So this, in some sense, it sort of, it exemplifies the standard way of how do you make robotics work right now. So the standard way or the sort of recipe for success right now is to structure the environment of your robot really well, and then give your robot as much information as you can about the environment. And once you have that, then you are able to create algorithms that can make your robots perform really well in these type of structured environments. But let's say you have a different environment of sort. Let's say you have an environment of this sort, where you have a bunch of objects all scattered on the ground. And the goal is to create a robot or to have a robot clear this all up. So what that means is that you want a robot that can maybe sort of try to pick up all of these objects and then store them away. Now, this is such a simple task that even a small 5-year-old child should be able to solve it. But for our state-of-the-art robots, this is still extremely challenging, right? Like I think if we had a robot which could solve this, a lot of parents all around the world would be like really, really happy. So one of the reasons we're not able to do this is because it's really hard right now to create robots that can effectively deal with unknown environments and unknown objects. And this ability to sort of work in an unstructured environment is really, really important. So it's not just important for this environment, but there are several real world environments where we actually want this to work. So this is a video from Ari. Real human homes look like. They are messy, they are diverse, there are a bunch of objects all around the place, but we as humans are still able to function really well in these environments. Okay, so how do we create algorithms now to make robots also deal with these unstructured environments? Now, fortunately for us, one of the biggest success stories in AI has been in creating algorithms that can effectively deal with the unknown. So here is a video of a detection system on a self-driving vehicle or on some road data. And what you can see that it's able to detect objects, segment objects, and it's able to do it even though it hasn't seen this exact video previously, right? So it's able to sort of learn from a lot of past experience, and then it's able to still work on this new video that it's probably not seen before. Now, in the same way, you can also create vision algorithms for detecting the pose of humans, for instance. So over here, it's the Gangnam style video. And again, this is a standard off-the-shelf human pose estimator, and it works really, really well, even though it's not seen these exact poses before. Now, the key to all of this success over here is the sort of new evolution that we are seeing of these deep networks, right? These like massive networks that can use a lot of information and can generalize to new environments that is not seen before. So the obvious next step to do is, okay, if you want to make robots as well work in the wild and solve these sort of unstructured environments or work in these unstructured environments, the simple strategy would be to just use these deep networks and just slap them onto your robot. But before we do that, we should look at another key aspect of learning. And so this key aspect of learning is data. And so why is this important? So as most of you know, before the AlexNet moment, right? So we had this AlexNet moment, which in 2012 we were able to show that you can actually achieve really good performance on image classification using a deep network. But before that, we needed a data set. We needed a data set like the ImageNet one, which came out 3 years before the AlexNet moment. And so this large-scale, diverse data is really important if you want to make your algorithms be able to generalize and work well in a new environment. Okay, but it's not any form of data. There are actually 3 aspects of this data which make it really important. And these are like 3 important aspects of data which we'll keep seeing over and over again. So what are these 3 aspects? The first one is size. You need to have large scale data because if you're using a complex neural network model, you need to be able to feed that model all of this large scale data so it does not overfit on small data. Next, along with the size, this data needs to be from the real world. It needs to be diverse examples. So if you want to sort of learn a model of a cat, you do not show it just a single you do not show it multiple images of a single cat. You show it multiple images of multiple different cats in your own environments. And this allows your models to now generalize and work on maybe a new cat that the model has not seen before. Now, the third aspect of data is supervision. So in vision, we didn't just have like raw visual information. We asked human labelers to actually label these images. So what that means that if you have an image of a cat, there's a human label along with it, which says that this is an image of a cat. And then for an image of a dog, you have a label which says that, okay, this is an image of a dog. And now this, it provides the necessary supervision that we need to train our models in order to learn well from this data. Okay, so in my research, I focus on these 3 aspects of data. And in this talk, I'll show you how we can use these 3 aspects in order to build robot learning methods that can work better in the wild. So particularly, I'll be trying to focus on the third aspect, but I'll also go over the first 2 aspects in order to sort of set the scene in some sense. All right, so let's get started on the first part, which is how can we get large scale data in robotics? So in order to look at this problem, let's try to start with a concrete example. So here, let's say you have a robot and you want this robot to figure out how to pick up objects on a table. And so these objects are objects which the robot has never seen before. So how would you make your robot figure out how to grasp these objects? Now, one way is you could create a human labeled data set. So this is the example of the Cornell data set, where they have a human annotator who annotates exactly how to grasp every object in this image. And now this works fairly well, but one of the key challenges over here is that human annotations are actually pretty expensive. And it's especially expensive if you want to annotate a robotic data set. And this is because when a human sees an object, they are biased by their own ways of interacting with this object. And so you really need an expert robot engineer who can now label this. So because you need an expert, it makes it expensive. And if it's expensive, it limits the total amount of examples you can label. And if you have small amounts of data, it's very hard to train these large-scale neural network models. But do we actually need a human? Can we actually obtain these labels without using a human at all? So what we did is this thing called self-supervised data collection. And over here, what's happening is that the robot is applying random interactions on objects. So it's applying a random grasp on these objects. And since all of these interactions are random, they may succeed or they may fail. But so the key thing over here is that when it fails or succeeds, there's a force sensor in the robot's hand. And so it can now self-label. It knows if it's actually successful or it has failed. And we do this not just 1 or 2 times. It's done around 50,000 times over 700 hours of the robot. So here are like a few examples of the objects that this robot interacts with in a self-supervised way. Okay, so after this, we have so inside our data set, we have a bunch of positive examples where the robot succeeded. And in terms of the representation, we basically have the patch of the image, which is centered on the grasp. And this is accompanied with the angle of the grasp. Now, along with positive examples where the robot succeeded, we have a bunch of negative examples where the robot failed. And now once you have this positive and negative examples, we can just start training our network. So in our network, we have the input of an image patch. It goes into a simple architecture. It's modeled after the AlexNet architecture. And the output is the probability of grasp success given a specific angle of grasp. Now we train this model on all of the data that we have seen. And once it's trained, let's see how we can use it for evaluation and testing. So let's say now you have an image of the scene and you want to figure out how to grasp it, how to grasp the objects in the scene. So what you do is you first sample hundreds of patches in that scene. You feed them all into the network. And then you basically try to find the grasp which has the highest likelihood of success according to your model. And once you find that patch and grasp which has the highest likelihood of success, since you know where all the patches came from, you can then apply this grasp on the object. So it's a pretty simple way of testing testing this type of model. So here is an example of this robot interacting with a bunch of objects that is not seen before. And so over here, again, note that most of these objects are in a cluttered environment. So it's not just object and all white space behind it. And one of the reasons it's able to work well over here is because it's sort of seen a lot of this examples in the past. So it's able to now generalize from all of those examples and then work on these new objects that it's not seen before. So at this point, are there any questions?
Yeah, one quick point of clarification. So the input here is just a monocular image stream?
Yeah, so over here, the input is just one image. So on the hand of the hand of the robot, there is a camera. So what happens is that the hand, it first goes on top of the table. It takes an image of the table. It does all the grasp learning stuff. It does all the evaluations of the grasp, and then it executes the grasp, which has the highest probability of success. So it's not a closed loop. It predicts the grasp, and then we use a motion planner in order to go to that grasp.
Okay.
After it predicts it, yeah.
And so is there some prior about like the height of the table or something like that?
Yeah, so over here, what we assume is that all the grasps are going to be planar. And so they're all going to be on the table. And so that really helps us over here because now the search space is much smaller. So instead of doing a full 6D grasp, we are going to do only a 2D grasp. And for these type of for like these type of environments, it works fairly well. So I think our best models, it gets us around like 80% success rate when it works only on the plane. So if there's an object which can be grasped on the plane, we're able to get around 80% with our best models. But then now if you have like a general object, which is in a general 6D pose, we'll not be able to use this model there.
Cool, thanks.
All right, so this idea of using large scale robot learning, we're not the first to do this. Or actually, they're not the only ones to do this. There are more people who have also looked at this idea. So this is work from Google Brain, which in some sense takes this idea 10 times forward, right? Because they have multiple robots now working in parallel. And when you have multiple robots working in parallel, you can get orders of magnitude more data. And now when you have more data, you can get better performance on this grasping task. All right, so I've spoken about how you can increase the size of your data sets by doing self-supervised labeling on your robot. And now I'll go to the second part, which is how do you get real world examples? Okay, so first of all, why do we want to, why is this an important problem? So if you see most robot learning works, including like my past work, you will see that a lot of these works, they either train in a simulation, a lot of these images are like fairly familiar. So there's a hopper, there's a walker over here, and a fetch environment. And so a lot of work is done in these simulators, but then the models trained in the simulations would never work in the real world, right? Because these environments are so far away from real world hardware and real world environment. Or instead of working in a simulator, it's done in a very constrained lab environment. So here for like most of our past experiments, we have this like plain white background, or in some other works, they have this like plain green background. And in both of these cases, if you learn a model over here, this model would never work if you, let's say, just like change the background of these objects, right? So in some sense, in either case, we are not able to create models which can actually work in an environment that is not seen before. So one option to fix this problem is to just, go into homes. So you just like take your robots and you go into homes and you obtain all of this diverse examples from these homes. But the challenge over there is that the standard industrial robots that we have, they're like really expensive, right? So let's say you wanted to go into 100 homes, and so for that you would need 100 of these hardware robots, which each of them, they cost around $35,000, which will just make it not scalable. So the first thing we need to do over here is to create a hardware platform which can do manipulation, which is a lot cheaper. So the first thing we did is to make this like low cost robot, which can sort of move around, and it has this small arm on it, and so it can interact with objects in the floor. And this robot now, it costs around $3,000, which means that we can scale it much better than if you used a more expensive robot. Okay, so in order to obtain a lot of data in homes, what we do is we just go on to Airbnb. We just book a few rooms over there, and we brought our robots. And so here are like few of our robots executing grasps inside the homes. So the grasps on the top left are actually from a trained model, whereas the ones everywhere else are all random interactions. All right, so in this way, we are now able to sort of use our low-cost hardware, move into homes of people, and sort of start obtaining diverse examples over there. But there's no free lunch, right? So if you're using a low-cost robot, there has to be some negative of using it. And over here, the negative is that there's more noise in the robot. So because of the actuator noise, your labels now from the self-labeling are not as great as it was with the industrial arm. And so what this means is that we had to create an algorithm which, apart from the standard how to grasp thing, which is on the top part, we also had to create a noise modeling part, which could sort of extract what the noise is of a specific robot and make a correction for that noise. And so I won't go into a lot of details over here, but at the high level, you have to create algorithms now which can sort of address this sort of noise inside your robots. All right, so to evaluate these models, what we do is we train in, I think, around 15 homes, and then we evaluate in 3 held out homes on objects that the robot has not seen before. And so what we find over here is that in terms of the performance, for a model which is trained in lab, which is like on a clean white background, the performance in these Airbnb homes are quite low. It's only like around 18%, which sort of makes sense, right? Like if it's not seen that environment in the past, it would not know about how to grasp or how to do anything in that environment. And now, like as we expect, if you use a model which is trained in homes, because it has now a large variety of environments, it's now able to generalize and work well in new homes that it's not seen before. So after this experiment, what we did is we can actually use the same models which has been trained on our low-cost robot and use them on our expensive industrial-grade robots. So what we do is we sort of use the same model on our Sawyer robot, and over here again we see that we're able to get high performance on the Sawyer robot. So something you'll notice over here is that the performance on the Sawyer robot is much higher than the performance in homes on our low-cost robot, and this is it's because of the noise, right? So because the actuators in this industrial arm are much better, they are more accurate, so all the grasps are better on the Sawyer robot. So here are a few examples of the grasps which are in homes over here, which is at the bottom. So any questions at this point?
So yeah, like perhaps drawing on this performance improvement on a more expensive or more precise robot, do you think in general this is the case that if you train a model that is able to perform better on noisier data, does it necessarily do well on cleaner data, or like are there cases where this might not work out?
Yeah, so I think what happens over here is we are training one model across multiple robots. So in some sense, you're trying to learn a model which has maximal, so it has to have an agreement across all of these. So in total, we train over 5 of these robots. And so we have to learn a model which works for all these 5 robot hardwares, right? So I think if it was only on one robot, then there would be enough bias in that robot, which would make the model not work well on an industrial arm, which probably has its own bias in some sense. But ideally over there, you have much smaller bias terms in the noise because it's an industrial grade robot. So I think this is it's sort of like interesting question, right? Like at what amount of noise would the model like entirely not train? And thankfully over here, even though we have some amount of noise through our noise modeling networks, and just because our robots do not have a lot of noise, it still learns our models fairly well.
Cool. That makes sense. Like perhaps a more technical question, but feel free to like just push this to the end if that makes more sense. Like, how do you ensure that the 2 models that you have, one that predicts the grasp and one that learns the noise model, they are somewhat disentangled?
Yeah, so that's actually a training. So that's sort of like a training trick in some sense. So what we have to do is we have to first train one part, assuming that the other part is not there. And once that part has trained, so once the network for the prediction has trained, then only then we introduce the noise modeling part. And so in that way, it doesn't end up just learning some like trivial solution.
Cool. Thanks.
All right, so let me move on. Okay, so now all of these models and even the hardware, we have open sourced this. So if you go to pyrobot.org, you'll be able to see these models and the hardware as well. So feel free to use it. Okay, so now I've spoken a lot about manipulation. Let me speak a little bit about our work on how to learn how to fly. And so over here, let's say you have a drone. The goal of this drone is to figure out how to fly in an environment without hitting things, maybe like movable things like humans or immovable things like these walls and chairs over here. So how can we do self-supervision over here? How can we do self-supervised labeling over here? So what we do is that we take this drone and we randomly crash into different parts of the space. And so it basically, it takes off, it chooses a random angle, and then it moves straight until it hits something. And then we do this not just in this one environment. It's done over, I think, around 20 different environments. And in total, we have around 11,000 hits or crashes. And the whole idea over here is that once you see all of these modes of failure in some sense, you can now identify when these modes of failure happen when you wanted to sort of not crash. And if you can identify this well enough, you can then steer away from these modes of failure. So over here on our drone, we have a monocular camera, which can record RGB inputs. And we also have a accelerometer. And so we need this accelerometer because when we hit something, we need to see the readings of the accelerometer in order to know that if it has hit something or not. And so with this, when we are annotating our data, we annotate all the examples that the drone sees a long time before it hits something. We annotate all of that as a positive example. We ignore most of the data in between. And then all the data that we see right when it hits an object, we label all of that as a negative example. Okay, so in this way, we have a bunch of positive examples now where the drone was far away from hitting an object. And then we have a bunch of negative examples where you have this drone which was right about to hit an object. And then again, we have around 50,000 examples here. And once you have this sort of positive and negative experience, what you can do is you can just train a simple neural network now. So again, we have a network which looks very similar to the AlexNet architecture. And it feeds in an image, and then it's just going to output whether you're going to hit something or not hit something. And so once it's trained over all of these 55K examples, which you have seen in the past, in testing time, what we do is we feed an image it sees. If it's not going to crash, we just keep going straight. But if it's going to crash, what should we do over here? So what we do is we take the left part of the image, the right part of the image, and feed both of these into the network. And then based on the outputs, we can then choose if we want to go left or to go right. So again, it's a pretty simple way of executing this model in evaluation time. And here is a video of this drone, which is flying through this environment. Again, this is an environment it's not seen before. And so it sort of shows the generalization of this model in this new environment. So in this example, what you're seeing is there's a bunch of chairs, and this and the drone has to sort of maneuver through this like very small gap. It does feel like at the end of the corridor. So as it turns back, it bumps into the wall, but then after that, it makes its way through. So over here, you'll see a human, and again, it's able to sort of not hit this human. And one of our hypotheses over here is that it's hit like so many human graduate students in the training time that it now knows a model of humans and is able to avoid them.
So I have a question.
Yes.
So if, let's say you train on no yellow chairs and then you put a yellow chair, like would it hit it? Like how good of a generalization does it get?
Yeah, so in general, it's hard to sort of quantify how good the generalization is. So over here, what we did is we used a pre-trained network, and so I suspect that if it's if it's like a simple color change, it should be fine. But what we did over here is we actually tried to run this drone outside in the woods, and it did not work that well there. I think one of the reasons is that all the data we had over here was all indoor data, and so it didn't see a lot of a lot of examples that you would need if you were going outside. So, for example, it didn't see any leaves, for instance, because there are no leaves inside this building.
And like real quick, do you just like feed an image, or do you first learn some sort of attention mechanism to identify what's interesting and then run some, like, what was the general network structure?
So over here, there was no attention. It was just like an RGB image, a single RGB image. It goes through and it just outputs if it's going to crash or not crash. Now, after this work, there have been a few other papers which have looked at, so not from our group, but since we released this data, there have been a few ideas on sort of using, let's say, an optical flow, for instance, where if you use multiple images, you can use the optical flow to create an attention of what it should look at. And so there have been like a few ideas of that sort. Yeah, but like in this work, we didn't actually use any of this.
Thank you.
I also sort of had a question. How do you view this kind of approach in relation to RL? Because like, it's kind of similar in some sense that you're like allowing this agent to experiment in the real world, and then you're actually sort of like self-supervising some sort of reward function in some sense, like this is bad, don't do that. And now you've got this like relatively like heuristic policy that you've got here. But so would you see like, what do you see in your mind as the connection between like this kind of an approach and like an RL kind of approach?
Yeah, I think it's a very interesting question over here. So I think in most of this work, we try to frame the problem as a supervised learning problem. And so the goal over here is to take like a greedy action in some sense. So its goal is that at this time step, what's the best thing to do? Now, of course, it works well for an easy task like how to grasp objects or how to not hit into obstacles. But let's say if you want to do a much harder task, like let's say you want to learn how to make a meal, for instance. And over there, you would need to, in some sense, give, either if you're doing a supervised learning problem, you need to find a stronger way of obtaining this sort of a supervision, or you have to do something like an RL-based approach where you just have like a sparse reward at the end of it, which says, okay, yes, you have made a good meal or not, and try to sort of propagate all of those rewards back in time. So I think it sort of it depends on what sort of signal you can obtain from your robots. In this case, since most of our tasks are quite easy, we can just do normal supervised learning over here. But I think for harder tasks, you'll have to do something like RL. But on the other hand, with RL, you'll also need a lot more examples. And so if you want to do RL for instance, of how to fly in the real world, you would need like a prohibitively large number of experience. And so I think if you're doing like something like sim to real or something, I think RL would be a good option because then you can get large scale data.
Cool, thanks.
All right, so I've spoken about how you can obtain large scale experience and how you can get diverse examples as well for your robot. And then in the third part, which is going to be also the final part of the talk, I'll speak about how you can obtain more supervision. And sort of like it connects back to EM's point in some sense, where if you have a hard task, it's harder to use these type of methods. Okay, so as I mentioned before, let's say you want to solve a harder task. Let's say you want to learn how to make a meal or something of that sort. Now over here, you have to do multiple steps. There are multiple waypoints in which you have to move through. And if you just use something like a self-supervised labeling or even like an RL method, you will have to sort of construct an environment in which you can obtain strong supervision at every time step. Because if you're not able to do so, it'll be very hard to learn from a sparse reward at the end of a trajectory. You'll never be able to sort of make a meal, for instance, if you just keep doing random interactions inside your kitchen and you hope to see a meal. And so what I mean by supervision is that, so if you're doing a grasping task, the way we get supervision over here is through a force sensor in the robot's hand. And this force sensor, effectively, it gives us a weak label. So it just says, is this like a good grasp or a bad grasp, right? But now if you want to solve a harder task, you'll have to get this sort of information at every time step. And this is just not a feasible option, right? Because it's hard to sort of instrument your environment to obtain this positive or negative signal or feedback. And so how can we go about solving this problem? So one way that humans solve this is through imitation, right? So we know that humans, we like to imitate things. And here is a video of the small baby who's watching a Rocky movie and is imitating the moves that Rocky is doing on screen. And so in some sense, what's happening over here is that through imitation now, we are able to obtain a supervision at every time step. It's not just at the end of the trajectory that this baby is seeing a signal of, okay, this is a good motion or a behavior or not, right? And so using this idea of trying to imitate an expert is like a very strong idea over here. And this idea has been used a lot inside robotics. So in robotics, how do we usually get these demonstrations? So the standard way of obtaining this is to do a kinesthetic demonstration. So over here, what happens is that you have a human user who's going to hold the arm of the robot and then move the robot in a way in order to solve the task. And so through this, you're able to obtain the sort of like very dense amount of supervision at every step, because you're sort of showing it what it needs to do at every time step. But there's also a limitation over here. And the limitation is that it's really, really hard to sort of show a demonstration, right? Because for those who actually try to give a kinesthetic demonstration, this is like extremely hard. It's very unintuitive most of the time. But I think like a bigger limitation over here is that these robots now are always inside a lab environment. And so it restricts the amount of diversity that you can see in these demonstrations themselves. So another option is to do some sort of teleoperation. So now instead of holding the arm of the robot, you can have like either a joystick or a VR controller, and you can use this in order to move the robot and show it what it needs to do at every time step. But again, over here, this is still expensive. And again, it's limited inside a lab environment, right? Because you need to have all of this mocap cameras and stuff, and then again at the end of the day, it's the robot that has to show the demonstration. Okay, so what we have done is to create a new framework in some sense for visual imitation learning. So over here, what we do is we use an assistive tool. So one example of an assistive tool is a reacher grabber. So on the reacher grabber, you have these two fingers at the end, which can open and close. And we have a camera, which can record visual observations. Now on the robot side, we also can make a reacher grabber as the end effector. So even over here, the actuation at the end of it is still a reacher grabber. And again, we can have a similar camera. So in some sense, we have the same observation space and the same action space on the robot. And what this means now is that you can just use this reacher grabber and move around and effectively obtain a demonstration for the robot. Okay, so this sort of idea was actually also introduced by Shuran Song, who I think is also going to be giving a talk. So if you're interested in this, please also see their work. Okay, so once you have this tool, one of the really nice things about it is that you can use this single tool in order to solve multiple tasks. So here you see a few examples like opening a door, opening a drawer, cleaning a whiteboard, and just doing like standard manipulation stuff that we are sort of interested in. But I think what is sort of even more interesting over here is that you can actually obtain a lot of diverse examples. So since this tool is really intuitive to use, each of these demonstrations, it only takes around like 4 to 5 seconds in order to do this. And you're not limited in being in a single environment. You can sort of use this inside your home, inside your friend's home. You can just go out on the street, and you can in effect use this anywhere that you want. Okay, so in order to show how useful this is, what we do is we look at two types of manipulation tasks. The first one is a pushing task, where the goal is to push an object into a red circle. So we are using the red circle to show where the goal for the pushing is. The second task we look at is a stacking task. So over here, the goal of the robot is to pick up an object and to then stack it on a different object that is nearest to it. And so in terms of the demonstrations, it tries to go to the nearest object and then stack it on the next nearest object. Now for both of these tasks, we collect around 1,000 demonstrations each on a bunch of areed objects and in a multitude of environments. Okay, so now we still have another challenge. If you're doing some form of imitation learning over here, how do we obtain the action information? Because if we only have a visual RGB camera, we just have a stream of images, right? So the first step we do is we feed it into a structure for motion software package. So we use CallMap over here. And what this outputs is all of the actions at every time step. Like, what is the change in the end effector at every step? The next thing we do is that we train a finger prediction network. So given an input of an image, we label a few examples of where the of where the fingers are. And once we train this, we can use this network as a way to now label all of our data from our demonstrations. So now from this visual stream, we have a way of seeing how the end effector is moving and if the fingers are going to be open or closed. Then to train our robot now, what we do is simple behavior cloning. So what we do is we have a bunch of images. It's just simple supervised learning over here, where the input is the image, the output is the expert action. And at the end of the day, we train a policy which outputs an action given an input observation. And once we have this sort of policy, in evaluation time, let's say we have this new environment, we again just feed in the image, it goes through this policy, and then it outputs the action. We apply the action, we see the next image, and then we have like a closed loop policy over here. Okay, so how well does this thing actually work? So in terms of performance, on the pushing task, we get a performance of around 87%. And this is all on objects that the robot has never seen before. And again, it's able to generalize now since it's seen like 1,000 demonstrations of like 8 objects. On the stacking task, the performance is a little lower. It's around 62% over here. And this is primarily because this is also a much harder task. So here are a few of the failure modes. So on the left, in terms of pushing, what happens is that it keeps going in front, and then it says it wants to go right, but by this time it's reached the limit of the workspace of the robot. And so one of the challenges we have here is when a human is using this tool, they can like move around, but the robot is sort of clamped down in one place. So it has a restricted workspace. On the left, what you see is for the stacking task, sometimes it tries to close its fingers a little too early. And if it misses the object, since we're not like learning on the fly, it cannot make any new corrections into the model. And so after it fails, it just fails, and it'll not be able to do anything better than this. Okay, let's see how we are doing on time. All right, still have some time. All right. After this, we also have a study of how important the size of data and the diversity of the data is as well. And in both of the cases, what we see is that as you keep increasing the amount of data, the behavior cloning loss, it keeps going down. So the error rates, it keeps going down. And then we also see that if you increase the amount of diversity, so instead of just looking sequentially at your data set, if you shuffle all of the data and still use the same amount of data, you get higher performance and lower error. Yeah, and so effectively more and diverse data, it always increases our performance. Now, the next thing we do is we also add random augmentations in training time. So we try out a bunch of random augmentations, like having a color jitter, doing a random cutout on the image, having a rotation, having a reflection. So in terms of the reflection, what we do is we also reflect the action over here. So in some sense, it's an easy way of just having, it's an easy way of just getting 2 times the amount of data now. All right, and so for all of this, we see that all of our, at least most of our data augmentations help. For the pushing task, the color jitter and the crop, it helps the most. And for stacking, it's the reflection and the color jitter, which helps the most. All right. So in summary over here, we have a new framework where you can easily get demonstrations for humans in diverse environments. And then since it's the same tool, both in the demonstration and in the robot execution, we are easily able to transfer what has been learned from the demonstrations onto the robot. And since this is a closed loop policy, what you can do is you can apply like small disturbances, and this policy should still work there. So that's the video at the bottom. All right, so this is sort of my last slide. And if there are any questions, I'll be happy to take them now.
I have a couple of questions, but let's start with there's a question from the YouTube stream. So I'll just read it out. So, hi, do you think training with more realistic simulators with domain randomization, we can limit the need to train in real life? Because apart from noise, simulators may be able to simulate different environments also.
Yeah, so this is actually a very interesting question. And so I've done like a little bit of work with this domain randomization inside a simulator. And I think a challenge over there is that you need to know a priori what is the space of randomizations that you'll need. So for instance, if you know that it's only going to be a change in the lighting, then sure, you can easily randomize all of the lighting during a training time. But the challenge with that is that if you increase the space of randomizations in training time, you're essentially learning a single policy that you want to work everywhere. And so you will end up with a more conservative policy now, because it's trying to increase the rewards or increase the performance on every on every single randomized parameter of the environment. And so in this case, what you're doing is you're going to sample environments now exactly from the distribution that you want your robot to actually work in.
Yeah. Yeah, I was curious your take on the simulator things, but I also had a question about the last part of what you were talking about. So I'm sure you probably know that like a limitation of behavior cloning is like that your demonstrations are optimal, and so if you kind of diverge from that optimal demonstration, then it's unlikely that you're going to be able to recover, because you have no, like, this is why Dagger and these other kind of like online imitation learning things exist. So I was like thinking about that, and I mean, what you've done with the building of this tool is like extremely clever. But it doesn't, or I can't think of a way that you could easily like interleave the operation of the robot and the human together in a way that you could do this kind of like online imitation learning. I don't know. Have you thought about that at all? And
yeah. So I think this is like so when we started doing this was like a clear thing which we'll have to do more work on. So I think it's a very important thing to think about. So the way I think that it can sort of improve is maybe not through a online learning based approach, but more through, let's say you're doing some sort of inverse RL or something. So I think that is probably an easier way to train. So effectively, once you see what the visual observations are that the human is showing you, you can create a reward distribution and use reinforcement learning to then increase the reward so that it goes closer and sees the observations that the human has shown. I think in terms of this, so if you're using something like LE operation, it's a lot easier to sort of interrupt the robot and show what the right action is. But over here, since we are trying to, in some sense, decouple the human information with the robot actions, it becomes harder to do. So there's an advantage and a disadvantage. And I think in order to make it learn on the fly, it'll be a much better idea to sort of learn a reward function on these observations and then do RL to make the robot go and maximize that reward.
Yeah, I think that makes sense. Eric points out that human demonstrations aren't necessarily optimal. And I was also sort of thinking about this as well. Like, I assume that during the course of this work, you became pretty good at using that gripper thing, right? Like that, or the grad student or whatever who was actually like collecting the data got pretty good at using that gripper. But did you like keep the data, like the data in your data set? Was it really just people who are like really, really well trained at using that gripper thing? Or could you get like some 7-year-old kids to come in and try and use the gripper and then use all of that data of like them learning how to use the gripper as like part of the data set that trains the robot?
Yeah, so I think one of our advantages is that we only had one person collect all of the data. So it was the first author, Sarah Young. So she gathered all of this data. And so it means that you don't have multiple experts as well. So that helps. But even with that, we had to sort of, from our initial data, what we saw is that a lot of the motions that we were doing, it was not replicatable on the robot. So if I'm holding the stick and if I'm like moving around the table, this is something a robot is just not able to do because it's like stuck on one place, right? So then we had to be like, okay, now when you're trying to do something, you just like stay in one place and like act as if you're the robot in some sense and don't try to like, move a lot. So like even with the single person, we had to like, because it's still not exactly the same thing as a robot, we had to do some steps in order to make sure that how we are showing a demonstration is still replicatable on the robot.
I also wonder, yeah, sorry, I just have one more question, if that's okay. We're going over time, but I hope that's okay. So like,
yeah, it's fine with me.
I was wondering like how far you think you can push this idea. So like, what if it was a camera attached to a human hand? Like, so in this case, you've really constrained the like action space and the observation space to be very, very similar, which is, which is clever for sure. But do you think that, certainly there's a limit to the types of tasks you can do with one of those grippery things, right? Like, and so yes, you could go ahead and like try and get a shadow arm and start doing insane things with a shadow arm or whatever. But like, I just wonder, what do you think the limit is in terms of being able to like extract useful information using this kind of a modality, even if there is some like discrepancy between either the observation space or the action space? How robust do you think this sort of approach would be to those sort of like domain shifts or whatever?
Yeah, so I think we use this form of random augmentation, and what that helps is for like small amounts of shifts, right? So because the camera is not going to be exactly in the same place on the robot and like and on the tool. And so we have to do like some amount of random augmentations over there. But if you have a larger shift, for instance, I think over there you will have to start thinking about how you can learn a feature, for instance, which is the same across humans or the robot. So I know that Ankur Handa has been doing some really cool work where from hands, you can sort of like extract what the pose of the hand is. And once you know the pose of the hand, it's effectively like a robotic hand now. Right? So something of that sort is also maybe an interesting idea. But over here, I think like one motivation over here was that with this stick, we saw that there are like so many things you can, so of course, it's not able to do everything that a human hand is able to do, but it's still able to do so many tasks that our robots right now are not able to do. And so instead of like thinking about, okay, how can we make this reacher grabber more complex? I thought, well, okay, for all the simple tasks that it can do, can we actually create a robot which can actually solve all of those tasks. I think once we have that, then I think that's like also a spectrum of easy tasks. And from that, we can create algorithms that can hopefully work when we have like a more expensive hand as well. So at least that's like my vision for this project, and let's see how far it goes. But yeah, I think at some point we'll need to have these like full like hands, for instance. Right now, at least to me, it's unclear how easy it is to do it, just because they are like so expensive. And there's this thing where the more actuators you have, the higher the likelihood of failure. And so when you have these hands and you have like 20 odd motors on it, it's hard to run large scale experiments, I would say.
Yeah, that all makes sense to me. Thanks.
Since we're just running over time, like I'll perhaps end with one general question, about the 3 pillars that you currently have on your slide. Mm-hmm. If you had to pick just 2, which 2 of them would be?
It's a hard question, because if you remove a pillar, the whole thing falls down. So I would maybe say supervision right now. I think that is probably one of the most interesting parts, and real world. So I would say that the 2 latest things are the most important ones. Yeah.
Okay. Okay, so like in the interest of time, I guess this is a good time to thank the speaker again. And yeah, I'll also reach out to the other folks at Mila about Lerrel is gladly agreed to like speak to anyone that's interested. So I'll just reach out about that.
Awesome. Thanks so much.
Thank you for having me.
We have one of those PyRobot robots, by the way.
Oh, nice. Are they useful?
Yeah. Ray, my student, he was on the call. He might still be here. Ray Wiatno was the primary person who was doing that. But we got it to pick up duckies and stuff like that.
Nice. Yeah, I still need to buy one because I'm new here, so I've not been able to buy one yet. So hopefully soon.
Yeah. Awesome. Thanks so much.
All right. Bye everyone. Have a nice day.